So today I'm going to talk about the one challenge here. Then how do we embed these laws of physics into neural network? So that drove a huge challenge and drove many interests from the different communities. For example, funding agency DARPA and National Lab PNNL, and workshops and conferences are held in this topic. Also, academic institution are entering, and also Microsoft Research, and they are actively looking for AI for science. Then, natural question is, then why we want to embed physics into neural network? So to illustrate this point, let me play this video. So left is the ground truth, and the right is the prediction. So I'll play this video. I hope you figure it out or notice something is not quite right on the prediction side. Can anyone notice something is not quite right on the prediction? You may see that some of the particles doesn't obey the simple law of gravity. So the setup is the same, similar to what Dongbin presented, but slightly different manner, so that the way I'm approaching is not based on the flow map approach, but rather approximating or learn the right-hand side of this autonomous dynamical system. So suppose we have the following autonomous dynamical system, z dot equal to f of z, where f is unknown function, so that we want to approximate or recover the right-hand side using some of the trajectory data we might have. So the typical approach is, all right, let's approximate the right-hand side using data and the neural networks. So the right-hand side being modeled as a neural network. Here, theta represent the neural network parameters. So typically, how we do that is, for given theta, we generate trajectories from this artificial dynamical system, z dot equals to neural network. Then from that model, we can generate the trajectory. Then we have two different trajectories so that we measure the discrepancy in a natural way and minimizing it. And the minimizer would be our model for right-hand side. And this is called pure data-driven approach. Then question is then how to incorporate physics in this context. So what I'm going to show you is I will going to change and present how we change the right-hand side that incorporate the physics, which is the first and the second laws of thermodynamics. And in this context, I found that there is a so-called generic formalism developed by Gramella and Oettinger back in 1997, which is the textbook, that described the right-hand side should be modeled by four functions. That involves L, E, M, S. And here, E and S are scalar values functions, and each of them are known as energy and entropy, and L and M are matrix valued functions called Poisson and the friction matrices. But one of the most important constraints that four functions should satisfy are those four conditions. And those four conditions actually guarantees us to satisfy the first and the second laws of thermodynamics. So that's our goal. So design four neural network architectures that satisfy the four conditions, 1, 2, 3, 4, and that's the minimum condition. But second goal is to our model remain expressive. So let me explain what do I mean by expressivity. And the third one is the being flexibility, because in some cases you may know L or you may know E, etc. Then we want some flexibility so that you can incorporate available physics right away. So at the end of the day, what we are modeling is the right-hand side being modeled as the follows. And actually, designing neural networks, full neural networks, satisfying all three conditions, not that simple, so that we divide the cases. So first of all, we assume that L and M are known to us. Then the remaining goal is to design E and S, satisfying the full conditions, remain expressivity. Since if you look at the full conditions, actually third and the fourth condition doesn't involve E and S, so that we can just think about just the first two conditions. And our design are based on two observations. The first observation is the kernel observation. If you look at this degeneracy condition, L times gradient being 0, can be viewed as the gradient of S belongs to the kernel of L. That's a simple linear algebra. And the second observation is that the following. Suppose we have some projection operator P from D to D, and F is the neural network from D to R. Then the gradient of F composed the P, which is the projection, belongs to the row space of Jacobian of the projection. So basically, we are going to combining these two observations to guarantee the expressivity. So idea is we're going to construct explicitly the projection operator such that this is our neural network design. So standard neural network and some of the projection operator we get from the L operator. Then based on the observation 2, the gradient of S and N belongs to the row space of the Jacobian of this projection operator. Based on the first observation, if this is the same as the kernel of L, we can ensure the expressivity. So this is our general idea on how we construct the E and S. And this is how the network looks like. So basically, we have some projection layer, which is fully known because we know L. And then this is a standard fully connected neural network, and this is Scala valued. And that's our design for S neural network. And similar for E. And the second case, we do this some similar way, but slightly different. So now we assume that S and E are known. Then remaining goal is to construct matrix valued functions that satisfy full conditions and expressivity. And one key part is that both cases, and the first two conditions requires that the basis times some gradient S or basis times gradient E has to be 0. So one key part for us is to design some basis-like function exactly satisfy this, and the rest is actually the easy problem because we can model symmetric matrix and skew symmetric, then all comes to the difficulty is to construct right basis satisfying these two conditions. And as a matter of fact, this can be done quite easily from this following simple lemma. So this is a quite simple lemma, but plays the most important role in this work. So suppose S1 through Sn be skew symmetric matrices, and G is any differentiable function. And we are going to construct a Q matrix in the following way. So first row is the S1 times the gradient of G, and then we test to take a transpose. And the same thing for the other rows. Then it is quite easy to see that if you just multiply the gradient of G on the top of the Q matrix, then this is 0 because of the skew symmetric property of S1 through Sn. And this automatically ensures us to satisfy the two conditions that I mentioned earlier, so that the proposed architecture for S and E becomes the following. Then this is the architecture, so that this is the eigenvalue part being modeled as a neural network, and the basis part is coming from the skew symmetric matrices. And then this is our final outcome. And lastly, when everything is unknown, we can simply employ the neural network for S and E and follow the previous case to construct L and M. So, at the end of the day, what we did is we changed the right-hand side to GFIN that I just showed you. So first example is the two-gas container example, so that we have a dynamics which describes the location of the wall. So that in a container we have two gases, A and B. And the Q represent the location of this wall, moving wall, and the P is the momentum, and S1 and S2 are entropies of each gases, and which can be exactly written in terms of the generic formalism. And we compare our method. So our method GFIN shown as the red, and this green is called structure preserving neural network proposed by this JCP paper. And the GNODE is another one that's shown as the blue. And here I show the test MSE versus the time. And one thing I should mention is that our GFIN applies to all cases, case 1 or 2A, 2B, but the existing ones have some limitations. So lastly, one great feature about GFIN is its natural extension to model stochastic dynamics. So without doing any hard work, the formalism can be extended naturally to describe the stochastic system, so that mu drifted term can be modeled exactly the same way that we constructed our model in the deterministic case, and the diffusion part can be done in a very similar way. And as a result, since we requires the full conditions to be satisfied, then that automatically gives us the conservation of energy and satisfy the fluctuation dissipation theorem, which is quite important in modeling stochastic system. So here demonstrate the longevity equation, so diffusion of a single particle. And you can see that GFIN actually quite do a good job estimating the probability distributions up to probably time 0.5. We're starting from time 1. It captures some of the large peak, but accuracy decreases, but we don't really do a good job on the extrapolation, which is expected. But some are known to us. Obviously, we can do better, even extrapolation.